Good morning, all of you. Today I am going to make an audio recording for visual impaired students of physical chemistry book of Dr. S.C. Ketupal Pardeep book. The chapter name is Chemical Kinetics. 5.1 Introduction. During the study of various reactions which may be carried out in the laboratory or industries or may be occurring in the life processes or any other applied field, we are interested to know how fast the reactions occurs, that is the rate of reaction. We are further interested to know how the reaction occurs, that is the step in which the reaction occurs, called the mechanism of the reaction. Also, we are interested to know how the rate of reaction is affected by changing the concentration of the reactant or temperature or adding a catalyst, etc. The branch of physical chemistry which deals with the study of rate of the reactions, the factors which govern this rate and mechanism by which the reaction proceed is called chemical kinetics. Further, a chemist is not interested in the kinetic study of all reactions. For this purpose, the various reactions are divided into three categories. First, those reactions which take place almost instantaneously. Example, many ionic reactions like AgNO3 plus NaCl gives AgCl plus NaNO3. BaCl2 plus H2SO4 gives BaSO4 plus 2HCl. Second, those reactions which take place extremely slowly, for example, roasting of iron, combination of hydrogen and oxygen at ordinary temperatures, etc., are called such reactions which takes months or even years before any decable change occurs. Third, those reactions which take place at measurable speed between two extreme discussed above. These are a large number of reactions which take place at speed which can be conveniently measured. A few examples includes in this category are CH3COO, C2H5, ethyl acetate plus water gives acetic acid plus ethyl alcohol, CH3COOH plus C2H5OH, C12H22O11 cane sugar plus water gives C6H12O6 glucose plus C6H12O6 fructose. NH4NO2 ammonium nitrite heat in, uh, gives 2H2O plus N2. H2O2 hydrogen peroxide gives water plus a half O2. A chemist is mainly interested in the kinetic study of reactions belonging to this category only. Another question that immediately arises in our mind is why the speed of different reactions are different. An obvious reason is that a reaction involves the breaking and making of bonds, since different bonds require different amount of energies for breaking and different amount of energies are evolved when different kinds of new bonds are formed. The rate of different reactions are different. The instantaneous nature of the ionic reactions is due to the fact that these do not involve any breaking of bonds, as ions are already present in the aqueous solution. Lastly, it has been mentioned that all chemical reactions do not proceed in a simple way. Complications are caused in the study of rate of reactions when the reaction is reversible or some side reactions take place simultaneously. In the present chapter, we shall take up the different aspects concerning the kinetics of reactions. 5.2 Rate of reaction. The rate of reaction may be defined as the speed or the velocity with which the reactions take place, or the rate of reaction may be defined as the change in the concentration of one of the reactant or product per unit time. For example, consider the dissociation of PCl5 to give PCl3 plus Cl2. PCl5 gives PCl3 plus Cl2. Rate of this reaction is equal to decrease in the concentration of PCl5 divided by time taken, or is equal to increase in the concentration of PCl3 or Cl2 divided by time taken. Unit of rate of reaction. Since the concentration is usually expressed in mole per liter and the time is taken in second or minute, the units of the rate of reaction are therefore mole liter inverse in inverse or a mole liter inverse, a minute inverse or atom second inverse, etc. for gaseous reactants and products. However, difficulty arises in stating the rate of reactions as above. This is because, according to the law of mass action, the rate of reaction depends upon the molar concentration of the reactants, and the concentration of the reactants keep on decreasing with the passage of time, while that of the product keeping on increasing. Therefore, the rate of reaction does not remain constant throughoutly. Thus, we should take the rate of reactions only at a particular instant of time. Hence, the rate of reaction is defined as follows. The rate of reaction at any time, called instantaneous rate, is defined as the change in the concentration of any one of the reactant or product per unit time at that particular instant of time. 5.3 Expressing the rate of a reaction. Since the rate of reaction is changing continuously throughout the course of the reaction, therefore, to state the rate of reaction at particular instant of time, a small interval of time dt may be taken during which the rate of reaction may be assumed to be almost constant. Suppose dx is the small change in the concentration of any one of the reactants or products during the small interval of time dt, then the rate of reaction may be expressed as rate of reaction is equal to dx by dt. Further, if the rate is expressed in terms of one of the reactants, a negative sign is attached to show that the concentration is decreasing. If rate is expressed in terms of any product, a positive sign is used to show that the concentration is increasing. For example, consider the reactant reaction A plus B gives B plus Q. The rate of the reaction may be expressed in any one of the following form. Rate of reaction dx by dt is equal to minus dA by dt is equal to minus dB by dt is equal to plus dP by dt is equal to plus dQ by dt, where dA, dB represents small decrease in the concentration of A and B respectively, and dP and dQ represent small increase in the concentration of P and Q respectively in the small interval of time dt. For a more general reaction of the type small a capital A plus BB gives P plus QQ. A unique value of the rate of reaction can be obtained by expressing the rate of reaction as follows. Rate of reaction is equal to minus 1 by A, dA by dt is equal to minus 1 by B, dB by dt is equal to plus 1 by P, dP by dt is equal to plus 1 by Q, dQ by dt. Remember that rate of reaction is always positive. Negative sign shows decrease in the concentration of the reactant, so that minus x is equal to plus a positive sign show increase in the concentration of the product. 5.4 Measurement of the rate of reaction. In order to measure the rate of reaction, the progress of the reaction is followed by studying the concentration of one of the reactants or products at different instant of time. The most common practice to do so is to withdraw a small amount of the reaction mixture 2 ml or 5 ml at different instant of time. Cool it down immediately to nearly 0 degrees Celsius to arrest the reaction, called freezing the reaction, and then find out the concentration of the reactant or the product by suitable method, usually by titration against a suitable reagent. However, this method is not preferred when some observable properties like volume, pressure, optical rotation, etc. change with time and can be observed directly at different instants of time without stopping the reaction. It is important to mention that factors like temperature, etc., which affects the rate of reaction, are kept constant during the kinetic study of the reaction. If concentration of one of the reactants is studied at different instant of time, and these values are plotted against the corresponding time, a graph of the type shown in figure 5.1 A or B is obtained. The rate of reaction at any time may be studied by either of the following two methods. First, a tangent may be drawn on the curve at a point corresponding to the time at which the rate is required. The slope of the tangent, which then obviously gives the rate of reaction at that time, because slope is tangent theta is equal to OB by OA is equal to delta x by delta t is equal to dx by dt. Second, the small change in concentration dc corresponding to small interval of time dt may be noted directly from the graph. Then, assuming that the rate remain constant during the small interval of time, the rate may be calculated as dc by dt. If the concentration of one of the product is studied at different instant of time and the value are plotted against the corresponding time, a graph of the type shown in figure 5.1 is obtained. The rate of reaction at any time is obtained by finding the slope of the tangent to the curve at that point corresponding to that time as shown in figure 5.1. 5.5 Factor influencing the rate of reactions. The rate of reaction depends upon a number of factors. A few important out of these are as follows. First, nature of the reactant. Second, concentration of the reactants. Third, temperature of the system. Fourth, presence of a catalyst. Fifth, nature of solvent. Sixth, presence of radiation. Each of these factors is described below one by one. First, nature of the reactant. To understand how the nature of reactants plays an important role in influencing the rate of reaction, let us consider the following two examples. A. Oxidation of ferrous ions and oxalate ions by acidified KMnO4 solution. Both reactants are similar as represented below. MnO4 negative plus 8H positive plus 5Fe2 positive. Fast Mn2 positive plus 5 Fe3 positive plus 4H2O. 2MnO4 negative plus 16H positive plus 5C2O4 2 negative. Slow reaction gives 2Mn2 positive plus 10CO2 plus 8H2O. At the same temperature, say room temperature, the first reaction is very fast, whereas the second reaction is quite slow, as indicated by the rate of disappearance of pink color of KMnO4. In fact, in the titrations, the second reaction is so slow that heating is required. Thus, in the above case, even if the concentration of similar reactants are taken to be same in the two reactions and the temperature is also kept at the same, the rate of these two reactions are still different. This is obviously only due to the difference in the nature of reducing agents, that is Fe 2 positive ions and C2O4 2 negative ions. B. Oxidation of nitric oxide and carbon monoxide by air. This reaction may be represented as 2NO plus O2. Fast reactions gives 2NO2 at 25 degrees Celsius. 2CO plus O2 slow reactions give 2CO2 at 25 degrees Celsius. Thus, the above two equations are exactly identical in the balanced form, but still at the same temperature. The first reactant is fast, whereas the second is slow. Again, in this case, also clearly that the difference in the reactant rates difference in the reaction rates must be due to the difference in the properties of NO and CO. Second, concentration of the reactants. As the reaction proceeds, the reactants are consumed, therefore, the concentration of the reactant decreases with the passage of time. It is observed experimentally that the rate of reaction also decreases as the time passes. This clearly indicates that the rate of reaction is directly related to the concentration of the reactant. The variation of the concentration of a reactant and hence that the rate of reaction with time may be represented graphically as shown in figure 5.2. That the rate of reaction depends upon the concentration of the reactant species is further confirmed from the simple example of rusting of iron. Rusting of iron is faster in the rainy season when the concentration of water vapors in the air is higher than in the dry weather. Third, temperature of the system. Temperature Temperature of the system. Temperature has a very significant effect on the rate of reaction, so much so that a rise in temperature not only increases the speed of reaction but in many cases it exactly initiates the reaction. Thus, to study the effect of temperature on the reaction rates, two types of cases are observed. A. For most of the reactions, the rate of reaction increases with rise of temperature. As a rough rule, in general, the rate of reaction becomes nearly double or sometimes even trebly for every 10 degrees Celsius rise of temperature. It is really a fantastic observation because the number of collisions increases only by about 2% for 10-degree rise at ordinary temperatures, where the reaction velocity may increase by 100 or 200% or even more. B. A large number of reactions are known which do not take place at room temperature but occurs readily at higher temperatures. Example, reaction between hydrogen and oxygen to form water takes place only when an electric spark is passed. Similarly, Similarly, it is well known that a coil can be kept in oxygen for years without burning them, but once the ignition is initiated, it goes until the whole of coil burns away. The above observations are explained on the basis of collision theory. According to this theory, substances react because the molecules collide with each other. Thus, threshold energy may be defined. Threshold energy may be defined as the minimum amount of energy which the colliding molecules must possess in order that the collision between them may be an effective collision. The concept of effective collision and threshold energy is just like the fact the some damage occurs to the two colliding cars only if they have a certain minimum speed. If they collide with a speed less than this speed, no damage may occur to the car. The two types of case may now be easily explained as follows. Explanation of the increase in reaction rates with increase of temperature. The different molecules of the reactants do not possess the same energy. If the energies of the reacting molecules are plotted against the corresponding fractions at a particular temperature T, a curve of the type shown in figure 5.3 is obtained called maximum distribution of energies. In the figure, ET represents the threshold energy. The shaded area represents the fraction of molecules with energies equal to or greater than the threshold energy ET. The shaded area beyond ET now becomes almost double. This shows that the fraction of molecules possessing energy equals to or greater than the threshold energy becomes almost double. Hence, the rate of reaction also becomes double. Explanation of non-occurring of the reactants at room temperature and occurring at higher temperature. At room temperature, there is no molecules possessing energy greater than the threshold energy, and so there is no reaction. What temperature is increased, the molecules of the reactants absorb heat energy, and thus a number of molecules starting attaining energy equal to or greater than the threshold energy, and hence the reaction starts. Activation energy is equal to threshold energy minus energy actually possessed by the reacting molecules. Thus, in order to the reactant may change over the product, absorb some energy and thus cross a barrier called activation energy barrier. Considered a hypothetical gaseous reaction, A2 plus B2 is equal to 2AB. In order that the collision between the molecules A2 and B2 may be effective, they must first from a tertiary intermediate called activated complex. In the formation of this complex, the bonds in the A2 and B2 are loosened and new loose bonds between A and B are formed. Thus, the formation of A B molecules may be represented as follows: A2 plus B2 gives AABB, intermediate activate complex gives 2AB. Thus, the energy barrier corresponding to the formation of an activated complex, hence activation energy, may be defined as the difference between the energies of the reactant and thus the activated complex. Another important result that follows from the above discussion is as follows. Those reactions which otherwise looks to be similar but have different rates can be explained on the basis of the facts that their activation energy are different. The lower the value of the activation energy, the higher will be the rate of reaction. Mathematically, it is observed that the fraction of molecules having energy equal to or greater than E is equal to e power minus E by RT. Hence, if G is the collision frequency of binary collisions, that is the total number of binary collisions per second per liter, number of effective collisions may be Z e power minus E by RT. Hence, the rate of reaction is equal to Z e power minus E by RT. This is because the rate of reaction depends not only upon the energy factor but also the orientation factor. That is, the colliding molecules must have proper orientation at the time of collisions. Rate of reaction is equal to P dot Z e power minus E by RT, where P is the probability or steric factor for presence of catalyst. A catalyst is a substance which increases the speed of reaction without itself undergoes any chemical change. For example, decomposition of KClO3 is greater accelerated by the addition of a small quantity of MnO2, which itself does not undergo any chemical change during the reaction. Fifth, nature of the solvent. In terms of a dielectric constant of the solvent, in case of ionic reactions takes place in solution for the given ions at a particular temperature, the rate constant K of that ionic reaction is found to vary with the dielectric constant D of the solvent according to the equation. Ln K is equal to A minus B by D, where A and B are a constant for given pairs of ions. B. In terms of polarity of the solvent, the polarity of the solvent affects the rate of reaction according to the following general rules. A polar solvent is accepted to accelerate a process in which a polar substance is a product and retard the process in which the product formed is nonpolar. On the other hand, if the acetyl of alcohol reaction between acetic anhydride and ethyl alcohol, the products are less polar than the reactants. Therefore, the effect of solvent is reverse of that in the first case. In the decomposition of a nitrogen pentoxide, the difference in the polarity between the reactants and the product of the rate determining step is so small that the rate is almost independent of the nature of the solvent. See, in terms of interaction of the reactants or activated complex with the solvent, it is found that the solvent affects the rate of reaction significantly due to the interaction of the reactants or the activated complex with the solvent. The effect of this interaction is to lower the potential energy of the substance by an amount equal to the energy of solvation. If one or both the reactants are solvated but the energy of the reactants is increased, the rate of reaction will therefore decrease. If the decrease, which means lowering of the required activated energy. 6. The presence of radiation. Some reactions which do not take place under ordinary conditions take place in the presence of light. Example, the reaction between H2 and Cl2 to form HCl. Such reactions are called photochemical reactions. The reason is that the radiation gives energy which absorbs by the reactant molecules and that the energy barrier is easily crossed. 5.6 Order of reaction and specific reaction rates. In order to understand what we mean by the order of reaction, consider the general reaction. A plus BB gives product. Experimentally, it is observed that the rate of this reaction may not depend upon all the A concentration terms of A and all the B concentration terms of B. Suppose experimentally the rate of reaction is found to depend upon directly proportional to concentration term of A and beta concentration term of B, then we may write rate directly proportional to A power alpha dot B power beta, or rate is equal to K into A power alpha B power beta first, where A and B are the molar concentration of A and B respectively, and K is the constant called velocity constant or rate constant if all the concentration are taken as unity. Hence, the rate constant may be defined as the rate of reaction when the concentration of each reactant is taken as unity. That is why the rate constant is also called specific reaction rate. Equation first is called the rate law. It differs from the law of mass action in the fact whereas the rate law states that the rate of reaction depends upon the concentration terms on which the rate of reaction actually depends as observed experimentally. According to rate law, rate is equal to A power alpha B power beta. According to law of mass action, rate is equal to K A power A and dot in B power B. The sum of the concentration terms on which the rate of reaction actually depends as observed experimentally is called the order of reaction. Thus, in the above case, order of reaction is equal to alpha plus beta, and the order of reaction may also be defined as the sum of exponents to which the concentration terms in the rate law are raised to express observed rate of reaction. Unit of rate constant for reactions of different orders. Rate dx by dt is equal to k concentration power n, or k is equal to dx by dt into 1 power concentration n is equal to concentration in divided by time into 1 by concentration n is equal to concentration 1 minus n time inverse. For zero order, n is equal to 0 is equal to mole liter inverse S inverse. For first order of reaction, S inverse. For second order of reaction, liter mole inverse S inverse. For third order, L square mole minus 2. Reaction of the zero order. A reaction is said to be zero order if the rate of reaction is independent of the concentration of all reactants. Obviously, for such reactions, the rate of reaction remains uniform throughoutly. There are two types of reactions which may found to be zero order. Thus, first, photochemical reaction. Photochemical reactions are those reactions which take place in the presence of light, photons. Many such reactions may have been found to be of a zero order. For example, the combination between hydrogen and chlorine in the presence of light may be studied by enclosing this gas in a test tube and inverted the tube into the trough of water. Second, heterogeneous reaction. A heterogeneous reaction means a reaction in which the reactant products and the catalyst are present in different phases. Some of these reactions have been found to be on the surface of gold and B by, de- by decomposition of ammonia on the surface of tungsten. The gaseous molecules of the reacting substance gets absorbed on the surface of the catalyst. The surface is thus fully occupied with the molecules of the reactants. Some of these molecules react to form the product. Expression for the rate constant for a reaction of zero order. For a reaction of zero order, A gives product. Rate is equal to minus dA by dt is equal to k, A naught is equal to k, or dA is equal to minus k dt. Integration both sides we get A is equal to minus kt plus I, where I is constant of integration. When t is equal to 0, A is equal to A naught is equal to I. Substituting this value of I is equation 2, we get A is equal to minus kt plus A naught. Kt is equal to A naught minus A. K is equal to 1 by T A naught minus A. Alternately, for a reaction of zero order, dx by dt is equal to K A naught is equal to K, or dx is equal to K dt. Integrating both sides, we get x plus kt plus I. When t is equal to 0, the amount reacted x is equal to 0, I equal to 0. Substituting in the above equation, we get x is equal to kt, that is the amount reacted inversely proportional to time. Characteristics of reactions of zero order. First, any reaction of zero order must obey equation 5, 6 or 7. As equation 5a is the type of y is equal to mx plus c, the equation of a straight line plots of a versus t will be a straight line with intercept a naught. Rate is equal to k, a naught is equal to k. Second, half-life period, that is the time in which half-life of the initial amount reacts. When t is equal to t1 by half, a is equal to a naught by half. Substituting in equation 7, we get t half is equal to 1 by k a naught minus a naught by 2 is equal to 1 by k a naught divided by 2 is equal to a naught divided by 2k. Thus, half-life period of a zero-order reaction is directly proportional to its initial concentration. If the initial concentration is doubled, the time taken for half of the reaction to complete is also doubled, and so on. 5.8 Reactions of the first order. A reaction is said to be of first order if the rate of reaction depends upon one concentration term only. For the reactions, A gives product, rate of reactions directly proportional to A. For the reaction 2A gives product, rate of reactions directly proportional to A only. For the reactions A plus B gives product, rate of reactions directly proportional to A or B only. Let us consider the simplest case. A gives product. Suppose we start with A mole per liter of the reactant A. After time t, suppose x mole per liter of it has decomposed reacted. Therefore, the concentration of A after t is equal to A minus x mole per liter. Then, according to law of mass action, rate of reaction directly proportional to A minus x dx by dt directly proportional to A minus x, or dx by dt is equal to k A minus x, where k is called the rate constant or the specific reactions rate of the reaction of the first order. The expression for the rate constant k may be derived as follows. Equation first may be rewritten in the form dx by A minus x is equal to k dt. Integration equation 2, we get dx divided by A minus x integrated to k dt, that is minus ln A minus x is equal to kt plus I, where I is a constant of integration. In the beginning, when t is equal to 0, x is equal to 0, putting this value in equation 3, we get minus ln A is equal to I. Substituting this value of I in equation 3, we get minus ln A minus x is equal to kt plus minus ln A. Kt is equal to ln A minus x. K is equal to 1 by t ln A divided by A minus x. K is equal to 2.303 divided by t log A divided by A minus x. Equation 6 is sometimes written in another form, which is obtained as follows. If the initial concentration is C0 and the concentration after T is Ct, then putting A is equal to C0 and A minus x is equal to Ct, equation 6 becomes K is equal to 2.303 divided by T log C0 by Ct. Kt is equal to ln A minus divided by A minus x. Putting A is equal to C0 and A minus x is equal to Ct, we get Kt is equal to ln C0 divided by Ct. This equation can be written in the exponential form as C0 divided by Ct is equal to Ekt, or Ct divided by C0 is equal to E minus Kt, or Ct is equal to C0 E minus Kt. 5.11 Reactions of the second order. A reaction is said to be of the second order if the rate of reaction depends upon two concentration terms. Two types of reactions are possible. First reaction involves only one reactant, that is the type 2A gives product for which the rate of reactions are directly proportional to A square is equal to Ka square. Second reaction involves two different reactants, that is of the type A plus B gives product for which the rate of reaction directly proportional to A B is equal to K A into B. The constant K in the above equation is called the rate constant for reactions of the second order. The expressions for the rate constant K for either of the above two types of reactions may be derived as follows. First, for reaction involves one reactant only, the general equation for such reactions is 2A gives product. Suppose the initial concentration of A is equal to A mole per liter, decrease in the concentration of A at an instant of time is equal to X mole per liter. Concentration of A at instant of time T is equal to A minus X mole per liter. Applying the law of mass action, the rate of reaction will be given by dx by dt directly proportional to a square, directly proportional to a minus x square. Dx by dt is equal to k a minus x square, where k, as already mentioned, is the rate constant of the second order reaction. Equation first may be rewritten as dx by a minus x square is equal to k dt. Integrate this equation, we get dx by a minus x square is equal to k dt. 1 divided by a minus x is equal to kt plus I, where I is the constant of integration in the beginning, that is at time t is equal to 0, x is equal to 0, as no substance has reacted at a 0 time. Putting this value in equation 2, we get 1 by a is equal to I. Substituting this value of I in equation second, we get 1 divided by a minus x is equal to kt plus 1 by a. Kt is equal to 1 by a minus x minus 1 by a is equal to a minus x divided by a into a minus x is equal to x by a into a minus x. K is equal to 1 by t x divided by a into a minus x. If the initial concentration is written as C naught and the concentration at any instant of time t as Ct, then A is equal to C naught and A minus x is equal to Ct. Substituting this value in equation 3, we get K is equal to 1 by T into 1 by Ct minus 1 by C naught. This is another form of the expression for the rate constant of second order reaction. Second, for a reactions involves two different reactants. The general equation for such reactions may be written as, if the initial concentration of A and B are same and each is equal to A mole per liter, then the method of derivation and the ultimate expression would be same as in above case. However, if the initial concentration of A and B are different, then the expression for the rate constant is derived as follows. Suppose the initial concentration of A is equal to M mole per liter, the initial concentration of B is equal to B mole per liter. Amount of A that reacts in time t is equal to X mole per liter. Then the amount of B that would react in the same time would be same is equal to X mole per liter. That is, at the instant of time t, concentration of A is equal to A minus X mole per liter and concentration of B is equal to B minus X mole per liter. Applying the law of mass action, we get rate of reaction dx by dt is directly proportional to A concentration and B concentration, in directly proportional to A minus x into B minus x, or dx by dt is equal to k A minus x B minus x. Whereas before k is the rate constant, equation 6 may be rewritten as dx by a minus x b minus x is equal to k dt. Resolving the left hand side into partial fraction, equation 7 may be rewritten as 1 by a minus b into 1 by b minus x minus 1 minus a minus x bracket close dx is equal to k dt. Integrating this equation we get 1 by a minus b bracket integration 1 divided by b minus x minus integration 1 divided by a minus x is equal to integration k dt, or 1 by a minus b ln a minus x minus ln b minus x is equal to kt plus I, or 1 divided by a minus b ln a minus x b minus x is equal to kt plus I, where I is the constant of integration, but at t is equal to 0 or x is equal to 0, putting this value in equation 8 we get 1 divided by a minus b ln a by b is equal to 1. Putting this value in equation 8 we get 1 divided by a minus b ln a minus x b minus x is equal to kt plus 1 by a minus b ln a divided by b, or k is equal to 2.303 divided by t into a minus b log b into a minus x divided by a into b minus x. Expressing in terms of the concentration directly, we may write a is equal to c naught a initial concentration of a, b is equal to c naught b initial concentration of b, a minus x is equal to ct a concentration of A after time t, b minus x is equal to ctb concentration of B after t time t. Equation 10 then become k is equal to 2.303 divided by t into c naught a minus c naught b log c naught b ct a divided by c naught a ct into b. Note an interesting result follows from the equation 10. If one of the reactant is present in excess, say B is in excess, B will be very large in comparison to A, so that A minus B is equal to minus B and B minus X is equal to B. The equation 10th become K is equal to 2.303 divided by minus bt log B into A minus X divided by AB, or k is equal to 2.303 divided by bt log A divided by A minus x. As b is in excess, it remains almost constant, so that the above equation can be rewritten as kb is equal to k dash is equal to 2.303 divided by t log A divided by A minus x. This is the equation for the first order reaction. Hence, when one of the reactants in a bimolecular reaction is present in excess, the reactions become kinetically of the first order. 5.14 Reactions of the third order. A reaction is said to be of the third order if the rate of reaction depends upon three concentration terms. The following three types of reactions are possible. First, reactions involves three molecules of different substance, that is A plus B plus C gives product. Second, reaction involves two molecules of one substance and one molecule of another substance, that is 2A plus B gives product. Third, reaction involves all the three molecules of the same substance, that is 3A gives product. The simplest case in the reaction of the last type, the expression for the rate constant of such a reactions may be derived as follows. Suppose A is the initial concentration of A and X is the decrease in the concentration of A in time t, then the concentration of A after t is equal to A minus X. Now, according to the law of mass action, the rate of above reaction at instant of time t will be given by dx by dt directly proportional to a cube, that is dx by dt directly proportional to a minus x cube, or dx by dt is equal to k into a minus x cube, where k is the rate constant for the third order reaction. Equation first may be rewritten as dx by a minus x cube is equal to k dt. Integrating this equation we get integration dx divided by a minus x cube is equal to integration k by dt, that is a minus x square divided by minus 2 into minus 1 is equal to kt plus I, where I is the constant of integration. Now at t is equal to 0, x is equal to 0, putting this value in equation 2, we get 1 divided by 2a square is equal to I. Substituting the value in equation 2, we get 1 divided by 2 into a minus x square is equal to kt plus 1 by 2a square, or kt is equal to 1 divided by 2 a minus x square is minus 1 divided by 2a square is equal to 1 by 2 into 2ax minus x square divided by a square into a minus x square, or k is equal to 1 divided by 2t into x into 2a minus x divided by a square into a minus x square, replacing a by c naught, that is initial concentration of a, and x by c naught minus ct, that is decrease in the concentration of a. Equation 4 may be rewritten as k is equal to 1 by 2t c naught minus ct 2 c naught minus c naught plus ct divided by c naught square c naught minus c naught plus ct square is equal to 1 by 2t c naught square minus c1 ct square uh, by 2t into c naught square c square ct square, or k is equal to 1 by 2t 1 by ct square minus c naught square. 5.18 Half-life period. It has already been stated in the predicting sections that the time taken for half of the reactions to be completed, that is the time in which the concentration of reactant is reduced to half of its original value, is called a half-life period of reaction. The conclusions shown about the half-life period T1 by 2 for reactions of different order, as discussed earlier, may be summed as follows. First, for reactions of zero order, T1 by 2 directly proportional to A, that is half-life period is directly proportional to its initial concentration. Second, for reactions of the first order, K is equal to 2.303 divided by T log 2 is equal to 2.303 divided by T into 0.3010 is equal to 0.693 divided by K. That is, half-life period is independent of the initial concentration. Third, for reaction of the second order, T half directly proportional to 1 by A. That is, the half-life period is inversely proportional to its initial concentration. 1 by fourth, for reaction of the third order, T half directly inversely proportional to 1 by A square. That is, half-life period is inversely proportional to the square of the initial concentration in general for reactions of the nth order. T1 by 2 directly proportional to 1 by A power n minus 1. 5.19 Molecularity of a reaction. According to collision theory, in order that a reaction may take place, the molecules must come close together and collide with each other. Number of atoms, ions, or molecules that must collide with each other simultaneously so as to result in a chemical reaction is called molecularity of the reaction. In case of simple reactions called elementary reactions, the molecularity is simple. The sum of the molecules of the different reactants as represented by the balanced chemical equation. A few equations are given below. First, decomposition of F2O2. The balance equation is F2O2 that gives F2 plus O2. Hence, the molecularity of the reaction is first and the reaction is called unimolecular. Hence, the molecularity of the reaction is first, the reaction is called unimolecular. Second, dissociation of Hi, the balance equation is 2Hi gives H2 plus I2. Hence, the molecularity is 2 and the reaction is called bimolecular. Third, reactions between NO and O2, the balance equation is 2NO plus O2 gives 2NO2. Hence, the molecularity is 3 and the reaction is called teramolecular. In case of complex reactions, that is reactions involving a number of atoms, ions or molecules of reactants in the balance equation, the chances for all the atoms, ions or molecules of the reactants to come together and collide are very rare. Hence, in such case, the reactions are supposed to take place in a number of steps. The slowest step is the rate determining step. The number of atoms, ions or molecules taking part in the slowest step, that is the rate determining step, is called the molecularity of the reaction. Thus, it is obvious that the molecularity of a reaction must always be a whole number, whereas the order of reaction can be fractional also. However, in the most of the reactions, the molecularity of the reaction is found to be same as of the order, hence the two are used without any distinction. The example discussed in the next session will be clear this point more clear. 5.21 Distinction between orders and molecularity of a reaction. The main point of difference between the order and molecularity of a reaction may be summed as follows. Order of a reaction, molecularity of a reaction. First, it is the sum of the concentration terms on which the rate of reaction actually depends, or it is the sum of the exponents of the concentration in the rate law equation. First, in simple reaction, it is equal to the number of molecules of the reactants as represented in the balance equation. In complex reactions, it is the number of molecules involved in the slowest step. Second, it needs not to be a whole number, that is, it can be fractional as well as zero. Second, it is always a whole number. Third, it can be determined experimentally only and cannot be calculated. Third, it can be calculated by simple adding the molecules of the slowest step. Fourth, it is for the overall reaction and no separation steps are written to obtain it. The overall molecularity of a molecule complex reaction has no significance. It is only the slowest step whose molecularity has significance for the overall reaction. 5. Even the order of simple reaction may not be equal to the number of molecules of the reactants as seen from the balanced equation. 5. For simple reactions, the molecularity can be usually be obtained from the stereomeric of the equation. 5.22 Methods for the determination of the order of the reaction. The methods commonly employed for the determination of the order of reactions are briefly described below. First, by using integration rate equation. In this method, the initial concentration of the reactants and the concentration of one of the reactants or product at different instant of time are different determined experimentally, then either of the following two methods may be employed. First, substitution method. The prepared values of a and x or c naught plus ct are substituted into the integration form of the rate equation for the first order, second order and third order one by one. The rate equation, which gives the constant value of k, determines the order of reaction. Graphical method. As already derived, the integration expression for the rate constant for reactions of different orders are: for zero order, k is equal to 1 by t a naught minus a is equal to 1 by t c naught minus ct. For first order reactions, 2.303 by t log c naught minus c log ct. For second order, k is equal to 1 by t is into 1 by ct minus 1 by c naught. For third order, K is equal to 1 by 2t into 1 by ct square minus 1 by c naught square. By using a differential rate equation, this method is based upon the fact that the rate of reaction of the nth order is proportional to the nth power of its concentration, that is, rate of reaction dx by dt directly proportional to c power n, or r is equal to k into c power n, where k is the rate constant for the reaction and c is the concentration at the instant of time t when the rate is r. Hence, for the two differential concentration, r1 is equal to k c1 power n, r2 is equal to k c2 power n. r1 divided by r2 is equal to c1 divided by c2 power n, or n is equal to log r1 minus log r2 divided by log c1 minus log c2. Fractional change method, half-life period method. It has already been discussed that the time taken for a definite fraction, says half, of the reaction to be completed is first directly proportional to its initial concentration for reactions of zero order, second independent of the initial concentration for the reactant of the first order, third inversely proportional to the reactant of the second order, T is inversely proportional to 1 by a fourth, initial proportional to the square of the initial concentration for the reactant of the third order. T is inversely proportional to 1 by a square. T is inversely proportional to 1 by a power n minus 1. Fourth, Oswald dilution method. This method can be used for finding the order of those reactions which involves two or more reactants. The method is based upon the fact that the order of reaction does not depend upon the concentration of those reactants which takes in excess. Turn by turn, all has been isolated from the others. The total or overall order of reaction is the sum of the order found with respect to the different reactants one by isolation. For example, suppose a reaction involves three reactants A, B, and C. In the first case, B and C are taken in excess so that A is isolated. The order that thus obtained is the order with respect to A. Similarly, by taking A and C in excess, the order with respect to B can be found, and by taking A and B in excess, the order with respect to C can be found. Suppose the order with respect to A, B, and C are found to be alpha, beta, and gamma respectively, then overall order of the reaction is alpha plus beta plus gamma. Alternately, keeping the concentration of all other reactants constant, the concentration of one of the reactants is changed, doubled, tripled, etc. turn by turn, and the effect on the rate of reaction of the reaction can be determined. This is illustrated below with the solved 5.28. Effect of temperature on the rate of reaction, Arrhenius equation. The effect of temperature on the rate of reaction has already been discussed qualitatively in section 5.5, and in the various terms involved like threshold energy, activation energy, energy barrier, activated complex, etc. have also been derived therein. Quantitatively, the effect of temperature on the rate of reaction and hence the rate of constant key was proposed by Arrhenius 1889. The equation called Arrhenius equation is usually written in the form K is equal to A e power minus EA by RT, where A is the constant called frequency factor because it gives the frequency of collision of the reacting molecules. E is called the energy of activation, R is gas constant, and T is the absolute temperature. The pre-exponential factor E power E minus A divided by RT gives the fraction of molecules having energy equal to or greater than activation energy EA. The energy of activation EA is an important quantity as it is characteristic of the reaction. Usually, the above equation its values can be calculated as follows. Taking logarithm of both sides of equation first, we get ln k is equal to ln A minus EA by RT. If the value of the rate constant at temperature T1 and T2 are K1 and K2 respectively, then we have ln Ki is equal to ln A minus EA divided by RT1 equation 3, and ln K2 is equal to ln A minus EA divided by RT2. Subtract equation 3 from equation 4, we get ln K2 minus ln K1 is equal to EA divided by RT2 minus EA divided by RT1 is equal to EA divided by RT1 minus EA divided by RT2. ln K2 divided by Ki is equal to EA divided by 2.303 R T2 minus T1 divided by T1 T2. Thus, knowing the values of the rate constant K1 and K2 at different temperatures T1 and T2, the values of EA can be calculated alternately. Knowing the rate constant at any one temperature, its values at another temperature can be calculated provided the value of EA is known for that reaction. To test the validity of Arrhenius equation, let us reconsider the equation second. It may be written as ln K is equal to minus EA divided by RT plus ln A, or log K is equal to EA divided by 2.303 RT plus log A. This equation is of the form y is equal to mx plus c, that is the equation of a straight line. Thus, if we plot log k versus 1 by t is a straight line, the validity of equation is confirmed. This is exactly found to be so as shown for our typical plot for dissolution of HI in figure 5.19. Further, for equation 6, obviously we have slope of the line is equal to minus EA divided by 2.303 R. Thus, measuring the slope of the line, the value of EA can be calculated. Thank you.